Hello students, so today we'll discuss about some structural defects in crystals. Uh, so it's structural defects in crystals. Now, the two most important structural defects in crystals are vacancies and dislocations. Now, atoms, when they are atoms are in the state of vibration. So, two atoms, for example, in a molecule, biatomic molecule, they are never fixed. They are always in the state of vibration. Now, when we increase the temperature, when the temperature in this case is increased, the vibrations enhance, and so whatever may be their equilibrium positions, the atoms start to get displaced from their equilibrium positions, and we need to actually find out the magnitude of this effect. So if we take, say, at room temperature, if we compare some of the atoms, and we'll compare it in terms of frequency of vibration and let's say average amplitude of vibration. We compare in terms of these two parameters, frequency of vibration and average amplitude of vibrations, and we take up some atoms, and so this is expressed as in terms of per second. So, and this is expressed in terms of Armstrong. So if we compare some atoms, for example, we compare sodium, then aluminium, then copper, and then molybdenum. So sodium will have a vibration of 4 into 10 to the power 12, and it is 0.5 value here. Aluminum will have 10 to the power 12, and it will have value of 0.2 here. Copper, on the other hand, will have a value 6 into 10 to the power 12, and will have 0.15, and again molybdenum will have again 7 into 10 to the power 12, value of 0.1. Now, it has been observed that this a frequency of vibration, this is actually independent of temperature. However, as you can see here, the amplitude, this on the other hand, the amplitude on the other hand it will it increases with increase in temperature. Increases with increase in temperature. Now let's say a typical case of copper. In the case of copper, the amplitude near the room temperature near the room temperature this is 1/12, or this is half the value at melting point. And it is again interesting, it is twice the value at 0K. So this is one of the observations, and this is for this copper. Another interesting observation is, since the atoms interact with one another, they tend to vibrate. You can see that since the atoms interact with one another, they tend to vibrate in synchronization. They tend to vibrate in synchronism. And that means they have a certain thing called, something called wave motion. However, an interesting observation is that the wave motion of these elastic displacement in a crystal, they are constrained by periodic splitting of the atoms. So again, there is a, they are constrained by the periodic stressing of the atoms. Periodic spacing of the atoms. And so this actually leads to quantization and we have a term called, so you can say that this leads to quantization. We have quantized elastic vibration, is called phonon. Phonon is nothing but one of the quantized elastic waves. Another imperfection in ideal crystal structure is called an exciton. Exciton basically means a bound electron-hole pair. Electron and hole pair which are bound by chemical interaction. That means, suppose you have a conduction band and you have a valence band, and by some way this electron jumps and goes to the conduction band. So at this present condition, you have an electron here and you have a hole here. However, these are at the influence of one another, so still there is a Coulomb interaction between these two. So this actually what formed is an exciton. So they are bound even though they are separated. So this another way of explaining is that this electron to cross this gap, to cross this band gap, requires some energy. So if we consider the bound EK model, so we have the different billowing zone. So from the first billowing zone, it has to move on to this next second billowing zone, known as 2 pi by A. So 2 pi by A. So this forms the first billowing zone. So it has to cross from the first and go to the second one. This is K. Now this exciton, or this electron-hole combination, it moves to the lattice. It has the tendency to move through the lattice. And finally, its journey ends when it recombines with another exciton. So this is all about, and it is used to explain the photoconductivity and luminescence. So the conductivity and luminescence. These two are explained or can be explained with the help of this excitome. Now, there are various other structural imperfections in the lattice, and these structural imperfections can be classified as point defects, line defects, and surface defects. So in case of point defects, we have two types of defects. One is called the Frankel defect, or we have the Schottky defect. Now, a Frankel defect is one where a vacancy is created as well as an interstitial atom is created. That means we have atoms arranged in this fashion. Suppose there is absence of one of the atoms here, and it goes and sits, this atom goes and sits here. So this is what is called a Frankel defect. Schottky defect, on the other hand, is when there are two different types of atoms, positive and negative, and there is absence of one positive atom and there is an absence of a negative atom as well. So this is what is all about Schottky and Frankel. In comparison to that, when we are trying to explain the line defect, line defect on the other hand is absence of set of atoms. That means say you have atoms arranged in this fashion. You can see that in this case, in this column, these atoms are absent. So a half plane. So these are actually not one single atom plane. It's the absence of one plane of atom. It's called dislocation. And it is expressed by this sign here. So absence of this atom, what actually it will do, it will try to squeeze these atoms together. Okay, it will try to squeeze them. So stress is generated in this region. In this region, the stress is generated. So that is how we can present this application. So in another form, we can write that it looks something like this. and on application of force, this dislocation breaks bond with nearby atoms and forms bonds, so it shifts. So ultimately the neck shifts and goes to the edge. So this is where this plastic deformation, this is what is known as plastic deformation, the movement of dislocation on application of force. So this is all about this line defect. Whereas if you consider the surface defects, in the previous case, third one is the surface defect. Surface defects will come as grain boundaries. So you have nucleation of atoms, and we have different orientation of atoms. We have different grain boundaries here. So these areas are the grain boundaries, where the atomic, which is the interface between two atomic orientation phases. So these grain boundaries are also defects, and they are known as the surface defects.